So my name is Jumana, and I'm joined by Shemik. We both work at Arm. I'll be basically covering the first 10 minutes of this talk, and then I'll hand it over to Shemik. So I will cover the Arm top-down methodology for performance analysis and give you all an introduction to Arm telemetry solution. This is basically the backend or the data that we use for performance analysis that then gets realized through profiling tools. And Shemik will cover how we enable the Windows ecosystem with all these features. And he will demonstrate the technology that I talk about through WindowsPerf tool with some demos. So the problem we are trying to solve is really performance analysis. And the solution we have from Arm side is what we call Arm telemetry solution. It's an umbrella that captures all the solution components we need to conduct performance analysis on basically Arm CPUs. So if we look at the landscape of performance analysis, it's basically a very complex and tedious process to go about diagnosing performance of your applications. And it's normally a very iterative and complex process because you are working through a very complex stack starting from your top-level application all the way down to how the application is actually performing on the underlying platform. So when we look at that, let's say if you look at a very high-level application stack or at an infrastructure level, for example, let's say a big data stack or something like that, when we start to look at the performance from a top-down perspective, you have multiple layers to tackle. So for example, you are looking at whether you have sized your compute machines appropriately, whether you have correct I/O performance, etc. That can be done at a very high level. You could use profiling tools to figure out whether you're I/O bound, network bound, compute bound, etc., etc. Or if you look at your application itself, there are multiple layers there again. For example, you could be deploying parallelism. You could have multi-threaded applications, and then you need to know how you have distributed that application into threads, how they are engaging, etc. But then there's the next level where you're actually running all your applications on CPUs, and from that perspective, you then need to know how your code is executing on that compute, and how do you go about performance analysis from the perspective of efficiently executing the application or making sure that you're getting better user experience out of your application. So for this, there is actually an industry-proven technique called top-down methodology, which came out of an ISPAS paper in 2014. The idea is that we look at a CPU execution pipeline where you have already established or you are actually looking into your compute performance, but there is a requirement for a technique to understand how you go about understanding whether you are getting the best value out of the hardware, whether your pipelines are efficiently executing, do you have stalls, and then how do you connect that information to actually optimize your code. So that's known as top-down methodology, and it is a hierarchical approach of going from the top to understand how your cycles are being executed, whether they were executed efficiently, are there stalls, and if yes, what is the reason, which can then be attributed to the code that you have written to understand what can you do about it. So if you look at a generic CPU execution pipeline, we all know it fetches instructions, and within the microarchitecture itself, there is a decode process that decodes these instructions, and sometimes they are broken down into micro operations, which then get dispatched to the execution units. So from that perspective, we kind of divide this up into two different buckets, which is your front end is where your instructions are getting into the CPU for execution, and then the back end is what is executing. So this is a very deep pipeline, and you want to understand how do you tackle the problem of, from a workloads execution perspective, how the cycles are being used, and then if you know where the stalls are, to kind of break it down to if it is a front-end bound problem or a back-end bound problem, and then that definitely means your performance issues are attributed to different scenarios, and they can be tackled differently. So this really helps a user for to walk that path, right? So from ARM perspective, we have developed telemetry solution to help us solve this problem where we provide that methodology, but of course the methodology is realized through the hardware events that we can capture from the CPU that helps us to get the data we need to build this. And we have also developed a standard framework as well as some low-level tools that help us to demonstrate this. So of course there will be high-level tools that are out there, like for example Google Perfecto or Windows Analyze tools and so on. That's where you get a high-level GUI. But this is kind of the back end of what you actually see in a profiling tool to help you analyze your code. So to give a very quick example or a layout of how we go about this and how does a microarchitecture look like. In the previous slide, I showed a simple example or a pipeline that a modern CPU would have. But this is an example, a diagram of a Neoverse CPU microarchitecture, which is in our servers as well as just now in the keynote we heard this is also going in the automotive SOCs. So at a high level, or it's not really high level, there's a bit more detail here, but this is just the breakdown of how our Neoverse microarchitecture looks like. It has components like you have your branch predictor unit, which is helping you fetch the instructions. In ARM side, we have the branch prediction running ahead of the rest of the pipeline, and that's basically predicting the control flow within the code so that you can get your instructions in the right order, right? And sometimes you make predictions when you have branches, which is basically the where your code could diverge. Then you have your instruction cache from where, which is where you are fetching your instructions to. Fetching your instruction from. Basically, the cache has the instructions that you fetch from your memory system. Then you have the decode, like we discussed. And then the decode unit will break down those instructions into micro ops that the backend can execute. And the backend, from out of order perspective, has units like reorder buffer or rename, which really helps with the out of order execution. But then the dispatch unit and the issue unit helps with issuing the operations to the respective execution engines. So for example, here you have integer issue queue, which basically issues all the arithmetic operations. The floating point or the SIMD issue queue dispatches issues the instructions to the floating point unit or the vector units, and the LSU issue queue dispatches your instructions or issues your instructions to the load store unit, right? So that's kind of the high-level breakdown, and then both the data and instruction side has the level 1 caches that are dedicated for data and instruction, but then they all share the memory subsystem where we also call the L2 unified cache or the TLB to be shared between the instructions and data. And then then that shares the rest of the memory subsystem where you could have a cache inside your interconnects or to the DRAM. So I didn't talk about TLB, but that's another path where when you are executing in virtual memory, you do need a translation unit or MMU that helps you with the virtual to physical address translation. And that is also part of this pipeline where you could have a stall. So high level, this is kind of the view of a microarchitecture. This is the pipeline that you're executing on. And all these units could be executing in parallel, but we still want to understand if one of this part of this pipeline is stalled, what is the reason, and then see whether we can fix it. So next thing to note from a background perspective is how do we go about analyzing them? So what's really happening in the hardware is we have something called PMU, which is a performance monitoring unit, which helps to collect events that's happening in the microarchitecture. So all the units like the cache or the load store, crypto execution unit, etc., all of them have signals that measure key attributes about their specific execution, and they are hardware events that are exposed to the software. And they have their register codes to identify them, and then we have a mechanism through the PMU unit from software to go configure which events are interesting for us to measure, to then derive the metrics and to get to the methodology. And then perf tools like LinuxPerf or WindowsPerf that Shemek will talk about today helps us with counting this as well as sampling these events. In a way, we can start to understand what is happening in the microarchitecture and then try to see where in the code is that happening. And for some of the key use scenarios here where you would know, let's say if you have an iCache miss problem, there are techniques out there that will help you solve that. So at a high level, top-down methodology is really a hierarchical approach to understand what is going on. And it has multiple levels. And for ARM CPUs at the moment in production, we currently support only the level 1. But if you are aware of this, or if you look back at it, there are multiple levels that you can walk the tree to understand your bottleneck. But at least for what we have support for, the top-down level 1 currently will provide you from all the execution cycles you have spent, whether how much of that was actually retiring, which means it was efficiently executing. And then the others are whether you had stalls in the front end or the back end, or you had a bad speculation problem. So bad speculation basically computes or provides measurement of how many cycles were wasted due to a misspeculation in the branches that cause flush in the pipeline. So that is costly. And if that's happening a lot, you kind of know that you are basically jumping between different libraries or different parts of the code, and it's not really local from a page standpoint. So as we support only level 1, we provide another level, another stage in our approach, where we then connect. After you have identified the bottleneck from stage 1, you can go deeper into the specific resources. So as we saw before, we have events that are specifically measuring what's happening in different parts of the CPU. And for example, an ITLB or a branch unit, instruction cache, et cetera, right? So those have their own respective metrics, and then we provide guidance on if you land at front-end bound, then we recommend you can use the events that are in ITLB, branch, or instruction cache, because these are units that are specific to the front end. And then those metrics and events will help you go further into understanding what is going on in that end. But it could be a back-end problem, then you are looking at a different part. So, but this is basically a methodology that helps you to go through that process of understanding where the bottleneck is. So that's kind of the background. Chemik is going to demonstrate how all this works with software and tools. But just to understand that from ARM side, we're providing the solution for our target is to provide this for all of our ARM CPUs. We support Neoverse CPUs today. And we have built a standard framework for how we represent that data so that tools can use that. And it is available in this link I've shared. And not only that, then our goal from open source or ecosystem perspective is that we make sure that what we develop gets into the key OS profiler tools. So in this case, I think I had a talk last year talking about how we enable this in LinuxPerf. Today we'll talk about WindowsPerf, and then Android ecosystem has Android Simple Perfs, for example. And then to demonstrate how we can do this, we built a top-down tool from ARM, which is also available at this space, which basically will demonstrate how you can characterize workload from a command line perspective with a simple Python tool, right? It doesn't have a GUI, but it runs based on the JSON schema that we have used, where we provide the specification in that standard framework, and they enable these tools. And of course, in the next part of the session, Chemik will demonstrate how WindowsPerf is enabling all this. Thanks. I will hand over to Chemik.
Let me get the clicker as well. Thank you very much, Jumana. A fantastic introduction. So we're going to focus now on top-down analysis with WindowsPerf and the telemetry solution top-down tool. We're going to have two examples. One will be with CPython. We're going to do the manual top-down analysis with the WindowsPerf on Windows on ARM machine. We're going to also show the top-down tool in action. It actually spits lots of data, so I'm just going to show you the parts of it that are actually critical for our workload we're going to work on. I'm going to give you some brief introduction to WindowsPerf as well. And I'm also going to show you some other tools that we developed to help people working with native ARM applications on Windows on ARM. Quickly, top-down microarchitecture analysis with WindowsPerf. What we focus on a PMU event-based analysis for the microarchitecture. We zoom in from the microarchitecture level deep down to the PMU events to understand what is happening for the different workloads. We support, of course, core PMU. For every core, ARM core, there is a standard PMU. It may be extended, and it's different for every silicon. You have to understand that for different, for example, Neoverse CPUs, you will have more, so PMUs evolve. You may have more complicated PMUs with more events. That's why telemetry solution methodology specifies for different CPUs, different metrics, maybe the same metric with the same name are defined with different events and have a little bit different formula. But that's actually opaque for this tool because we do import everything from the telemetry solution, from the JSON files and structures into our tool, so we understand for every core how the top-down and every metric and every event works. And we're going to use for the top-down analysis on that microarchitecture level. For stage one, exactly for top-down, we will use counting. We will count in a different, like in a front end and the back end, we will count for stalls and different events. And then we can zoom in for even instruction level understanding of the bottlenecks with samplings. When we're going to count specific events, we're going to overflow them, capture the interrupts, read the program counter, and see where in the source code exactly we are. I'm going to show you the examples from the command line, how we can do it by hand or with a top-down tool to a degree. So yes, the integration, like Jumana said, everything she said, we actually pull inside our tool. What we do is we take advantage of the standardized JSON format that the telemetry solution team is providing, which is actually fantastic, and it's defined, like Jumana says, there's a framework for this. So all the tools are future-proof, the top-down and WindowsPerf as well. What is interesting is that to perform this kind of analysis, one has to understand more or less what the microarchitecture is, but also have to understand the nature of the workload they are actually working on. Like Jumana said, you can do the performance analysis on a very high level of your application. For example, understand the startup. If there is lots of I/O, if something is CPU bound, maybe your libraries are opening sockets and doing some crazy stuff on the disk or whatever. But for this, we focus on the CPU, maybe grinding through an algorithm rather than a very high level view on what your application is doing in a cloud for 10 days. That's not what we intend to do. For examples, I'm going to do the CPython. Maybe it's more interesting. Manual top-down analysis and also the automated with the top-down tool. You can see the advantage of the manual one. You can see exactly how many events are happening and what's happening on the screen. But from the top-level view, you would like to run the top-down tool on Linux and on Windows. You're going to get the same results because we ported WindowsPerf for this tool. And the telemetry solution team actually helped me to patch it so it actually works on Windows in a very good way. I'm also going to have a little bit of talk about just a little bit about the WindowsPerf GUI and give you some very simple synthetic example for someone who will, for example, develop an algorithm in Visual Studio and they want to see how this looks like from the maybe top-down perspective. So quickly, why CPython? What it is a C implementation of Python. It's good because we can build locally natively on ARM CPython with all the DLLs, executables, the PE files. So we have all the symbols, DLLs, we can disassemble, we have the source code, so we can look at all those things and we can zoom into the even disassembly level. What are the prerequisites? Well, you have to do it on your ARM64 native machine, right? And you have to, for every analysis like this, you have to build your application yourself with a debug mode, or you have to be provided with executables and the PDB files, so the debug information files, so you can actually run this analysis. We did run for customers without having the source code. What they build us executables, the PE files, DLLs, provide the PDB files. Also, WindowsPerf is smart enough to read the PE files, dependencies to libraries, and actually can track. And I will show you with this example that we actually snoop inside the DLL rather than just into the executable. And of course, this demo is not to show you how to fix something in CPython. It's a synthetic example to show you how you can actually dig deeper. Because like Jumana said, it's really, really hard to do the performance analysis of a specific workload. It's always a different thing. And it's actually very hard to actually deduce what to do with this, what to do next. Sometimes the answer is very easy. Oh, I need to vectorize my loop. Sometimes just like that, or turn on some compiler flag I forgot to turn on. But sometimes it's a more complicated problem of a data structure, something like this. So let's go quickly with our examples. So we're going to start from the top. We're going to use the counting. On the top, you will always see a command we are running. So Jumana already talked about the top-down and the stage 1 and the stage 2, and because I read the documentation, I know in the stage 1 I can use the cycle accounting metric that actually WindowsPerf understands because we pull it from the JSON. So I can just say -m for metric, cycle accounting, so I can actually look at the front end and back end and how many cycles are being there stalled. You can see this at the bottom. We print here all the events for all the metrics for the group of, actually cycles accounting is a group of metrics, not a metric. It's just a group of 2 metrics. We can just run them on the CPU and we can see by calculating the CPU cycles versus the stall cycles so how many percent, what is the percentage of the cycles stalled at the back end or the front end. For this particular example, I'm running the CPython and I'm just trying to evaluate 10 to the power of 10 to the power of 100, which is a Googleplex, right? It's a very big number. It takes forever to count it. But I understand in Python, when I do this operation, I actually expect this to be integer, right? So if I see some kind of a floating point operation there, I'll be actually unhappy. Actually, will not see. But so someone actually did it correctly. Also I will understand, I probably can understand the structure holding this number as a result will grow. So I'm expecting there will be lots of memory operations as well. Maybe loads, maybe stores, maybe something else. Let's see. But I know because I ran it before, so I know what's going to happen. So also, where is the documentation why I have to read the JSON? You don't have to. There is a list command, just like in LinuxPerf. You can run it. It will detect your CPU and show you if you're on Neo version 1 and 2 or V1, and many more in the future. It will actually show you all the metrics, events, groups of metrics with the formulas as well. We are not showing here because it's a massive printout. But we're also going to add additional command, like a manual command, so you can actually inspect this. But I just want to show you how this basically looks like. There are cycle accounting. I can see the front end and back end are 2 metrics from this group of metrics. And also, I know at the back end, Jumana showed this kind of a stage 2. I can actually look deeper at the back end. And with the operation mix. Operation mix is basically, I can look at different speculations like load store, floating point, SIMD, and other major components of the execution of our process, or our workload rather, to see what's happening. I'm choosing this over everything else because I can run everything else, actually, one by one, by running it manually and with a top-down tool. And this is the most interesting one because it gives you some kind of a reasonable places to look deeper for your hotspot analysis. Just to let you know as well, all these metrics, group of metrics have nice names that Jumana's team prepared for us to read and understand, so you can read this and go deeper, go to the web page, read and try to understand how everything works. Again, please understand for every microarchitecture, for every CPU, if it's a custom CPU licensed by ARM directly, it could be a little bit different, if that makes sense. Also, lots of people are interested in Encore analysis, so not only PMU analysis, but also the Encore PMU analysis, the CMN, the mesh analysis. All those things are possible with WindowsPerf, but someone has to send us a patch to support this. So I can actually go and look deeper at the mix of operations. So what's happening is that operation mix is another group of metrics. All these metrics are part of this group. WindowsPerf, like LinuxPerf, is very smart. It takes all the events for all the metrics in this group, groups them correctly in the sets of events that we are putting inside the counters, so we can multiplex them at the same time. So we actually get a reasonable amount of information that is correlating. So all these events in all these metrics are actually correlate in time, right? So they are not random. They correlate in time. Also, Neo version 1, this is my example. I have only 6 PMU counters. So if I run maybe a metric, 2 events per metric, maybe 3 metrics, more than 3 metrics I actually run, I have to start multiplexing, which is actually fine. And newer versions of microarchitectures may have much more counters. I think already the latest cell phone CPUs have very many more events. But just to look at the output, we can see we run the same workload. It's also important. I run this workload all the time. It's the same workload. I run it multiple times, the static analysis. And it also has to do the same thing. It happens to people that they run a workload and say, it runs 10 seconds the first time and 5 seconds the second time. It's like, but what you are, it should always be the same. So you have to manage your workload in a way that is repeatable, right? You cannot have dependencies. It cannot open socket, wait for something. It's usually a compute. So from this, I can see there is lots of integer operations, lots of loads and stores. Usually stores and integers are here dominant. I have no crypto operations, literally zero, not even one event for crypto. Nothing crypto happens there. I have some also branch speculation there, but I may focus on maybe loads or integer operations or store. I'm actually happy that maybe there is no floating point operation, so no one's using double, for example, to count that number, that power. That may be good, maybe bad. This is the beginning of the same command. I can see all these metrics being shoved into the PMU, so I can get all the counters and all the values. Please note with every color, you can see that I'm actually grouping the events, and I'm actually putting the instruction speculate. So load speculate divided by instruction speculation is actually the metric value, maybe in percent. I'm shoving this in the same groups, so at the same time into the PMU. And because I have actually 6 counters, so you can see that without multiplexing this group of instruction spec, this one and this one, this is exactly the same value. And later this value changes because I'm multiplexing, I'm putting another group of events in. But when I scale, I actually get the correct value because I understand how I'm multiplexing, so it's a little bit moved. So actually I understand how it is. Our colleague Jong actually implemented the multiplexing this tool in the prototype. It's extremely useful. It doesn't actually make this kind of analysis more cloudy. Also in the future, when you are using this kind of analysis, you can start with, make this like a top level view, and you can go deeper looking at only the metrics you want to see on event counters that are actually running without multiplexing. If it's very important for you, you can do that. We are not running any extreme amount of interrupts as well, so we are not actually interrupt bound that much here. So this is, we actually can repeat lots of this. Well, it's repeatable. But we are using the use-stress micro benchmarking from Joanna's team also to evaluate that what we count with WindowsPerf is actually accurate for different metrics. But going forward, what we actually get from telemetry solution is all these metrics with all these events and all these formulas, and all those things are explained to a degree. Always look into your microarchitecture manual of your CPU to understand how many events that you have and how it is. PMUs always evolve. Also, we detect the version of the PMU. There are different versions and different small updates to the PMUs depending on your CPU. It might be that some events are not available on the client CPUs because they are smaller, but for server CPUs like Neoverse, they are available. Okay. And what I will do now, I already understood that maybe load speculation is something I want to look into for my workload. So I know that the LD spec is one of the events that are important for that metric, is actually the important one. So what I can do now, I can do start sampling. What sampling is, I take event of the group or events. I set register that is counting this event to certain value. And when this, I start counting, and when this register saturates, I get an interrupt, and I can actually inspect the program counter, right? And remember it and store this program counter. If I have a program counter, I have a debug information. I can also inspect inside the PE files, so executable files, DLL files. I have source code, I understand which function it is, which line of code even it is, and I will show you how to zoom in with annotate and disassemble that we build in to go even deeper. But this is enough for us to actually understand what this workload is doing and what is the dominant operation in this multiplication. It's the xmal, right, function that in a DLL in the CPython. So CPython executable is actually not doing anything except for just running a code in different DLLs. And it happens that in this Python 312 DLL, underscore means debug mode, right? So it's running this, and I can see there is a xmal function. Some kind of a symbol in this DLL is actually causing the most of the trouble. The Pareto rule applies. 80% of causality is somewhere there. So we can actually start investigating deeper with annotate and disassemble, which by just adding the dash dash annotate or dash dash disassemble to our command line, we are not changing that much. This is just a part of the output from our tool when we run it for 10 seconds, 30 seconds. We sample, we get the program counters, we get lots of line numbers, and hits are here program counters that actually hit around the line of code that we can inspect in the debug information. And we see in this long object.c, there is this function, this symbol called xmal in this library, in this executable. So we can actually now directly go to the source code and have a look, but we can also do something else. Also, we get information like this for all the other symbols that are available. We get for all that. We can also add disassemble. There is a caveat here I'll talk about in a moment, but what's happening is that I get this kind of very simple information. There is a source code. There is a line in the source code, and there is certain instruction address, and I can actually disassemble this function and go around that instruction and see what it is. The caveat is that PMUs are not perfect. They are not like SPs that we are trying to implement actually with WindowsPerf. There is a events kit, maybe 80, 100, maybe less, maybe more instructions. So what we are actually hitting here is not exactly the instruction causing a problem. Somewhere around this instruction, but definitely in this function, somewhere there is a problem there. It could be that 80 instructions around this address, you are still in a while loop, and actually in the source code we are in a big while loop that is performing this multiplication all the time, because that integer in Python is not a binary integer in a register like 60. It's just like a massive data structure that you just grind through with the while loop if you look deeper in the source code. What are the next steps if I do this kind of analysis? Well, I have to understand the workload. If I am a C Python developer, I'm going to look inside. I know the code. I know what's happening. Maybe there is nothing else I can do there. I can also inspect what's happening with the integer operations. That maybe some data structures maybe not as efficient as they could be. And I will definitely have this workflow when I run the static analysis. I change something, whatever it will be. It could be a toolchain flag. I can change the implementation a little bit, tweak my data structure, right? Change the order of something, simplify something, or have maybe a function that exactly targets this kind of operation. Maybe it's something people use common. I, of course, use benchmarking to do that as well. Time is very important in general. Just because I can see there are 15% stalls in the backend, and I do something, and this number may improve or not. Also, the time that we are not counting here is actually very important for your application when you're running. So how many cycles it actually takes to run your workload. Please remember the workload is usually some piece of code, a library, a module in isolation that you maybe mock some inputs, maybe mock some outputs to have this reproducibility. Usually for this kind of analysis, you always also you will actually make this workload so small it can fit on one core. Maybe it's even one threaded, because we are not talking about multi-threaded analysis here at all. It's just one thread, maybe many threads, but maybe on one core, everything is in one core, and we try to perform this analysis. So you can do all of those things and, wash, rinse, repeat. You can do all kind of to improve. Every workload is different. But we can do all the things I did, or almost all the things I did, at least the beginning, with the top-down tool that is available. So I ported the top-down tool to support process spawn, and with the parameters we're going to publish soon. It was very simple addition to that. This tool is easy to extend this tool. So you can run the same stuff with this tool, and this tool will spit a lot of data outside. All this stage 1, stage 2 metrics, group of metrics will be available there. You will see the stage 1, how many cycles, stage 2, all the microarchitecture metrics with all their units. Units are also defined in the JSON. All the things are defined. You see how many instructions per cycle, which is also very important. You can see actually not much is happening in this workload. It's a purely simple multiplication computation. So it's easy to see that this speculative operation mix actually gives us some hints that are actually useful. Yeah, I have a very simple synthetic workload example, just to show you that you may just develop your small function. You want this function to be very efficient. Maybe you are doing something, some computation, maybe new sort, you are inventing new sort, whatever, who knows. So you can have some kind of a function. For some reason, your toolchain is not doing vectorization. You maybe want to do that. So maybe you inspect your functions. You find this is the hot area with our tool. We have a GUI for this that Nether will present later. You maybe want to use some intrinsics to improve that loop or whatever the algorithm is. Rerun WindowsPerf through the Visual Studio extension, have some heat map, look at your code, measure some performance also with the other benchmarks that you may have. So in general, our team is also preparing the tools that are helping people to develop in well-understood environment on Windows on ARM. We have access to things like Visual Studio Code. You have also ETW, Extended Trace for Windows, and other things. We're going to talk about this later in different presentations, but I just want to show you that it's not only command line tool, it's not so alien and weird and different, but if you want to dig deeper, you probably want to go with a command line, but still you have access to the same information. This is for sampling. You have the information I just showed you. You have for sampling for the simple synthetic workload with some debugging information on the right side. It's fantastic addition to the Visual Studio. It's a plugin that our team is developing. Okay, so there are lots of blogs about different releases that we do and about WindowsPerf. And each time we have the release, we try to have a nice release note in a form of simple blog. There is also lots of resources in the learning path of ARM. There are lots of resources on the developer.arm.com. Jomana's team has lots of useful information there. Very good read about the top-down. I encourage you all to read through this. Even if you're not really a performance engineer, you should be really interested in understanding how others measure the performance, especially that ARM CPUs are all about performance, low power, right, and a good price. Yeah, like I said, for the telemetry solutions, you have lots of very interesting resources that also so all the metadata that Joanna talked about, all the JSON files are available on the ARM's GitLab. That is available. It's open source. You can download this data. We scrape this as well. We get this data in our tool. We import that. So we can get all the data in. And we also help to develop top-down tool. There another tool that just came up is the SP parser that allows you to parse the perf data from LinuxPerf and see the SPE output. That's going to be also useful for us for WindowsPerf as we're going to do the same thing. We're going to add the SP support. OK, thank you very much. Yes.
Could we use WindowsPerf or perf tools to identify context switches and what happens during a context switch? Does the performance counters, let's say I have a get time of day.
That maybe Jumana can answer, not me.
So context switch is not directly coming from the PMU events, but you measure it with other kernel events, like from system software side.
Yeah, so this kind of information on the high level, you probably want to get on Windows with the extended trace for Windows, when you get lots of different metrics and events that are coming from kernel and from the applications themselves.
So in this context of getting performance counters separately for,
yes,
say, let's say, get time of day, you have a user space component that has all these performance counters. Can you also provide the performance counters for the kernel space for the same call stack, like for the same application?
So that information is there from the kernel's traces. So I think from a tooling perspective, you'll have to get the kernel events, which we call as software events. This is hardware events, and you'll have to provide a tool where you bring those both data together for analysis. So this purely covers what hardware is counting and what's happening in the microarchitecture. Yeah. But kernel supports system software events, yeah, which includes context switch count. Yeah, it's a microarchitecture analysis with WindowsPerf or LinuxPerf rather than high-level analysis of the context switch and kernel events. But what Everton is working on actually is to
we can inject, he already proved that we can inject ETW events into the ETW stream, and we can use the Windows tools to actually visualize what we are talking about, the context switches and CPU activities, IOs, and we can correlate with the PMU events because we can just see them in the same context, in the same visualization tools. But microarchitecture analysis is already, we zoom so much that the context switch we are not that really interested in. We are interested in completely different things.
So one thing to note though is that at least I can talk from LinuxPerf perspective, right? We have the capability to go and count these per thread, per application, etc. So let's say if we were counting for a perf, I can talk from LinuxPerf perspective. I don't know if it's enabled in Windows yet. We can say perf, count these events, but only for this process. So those events are only counted when that process or the threads related to that process comes in context, right? But then sometimes we can count, if we count across the CPU, then regardless of what thread it's running, you will get overall what's happening in the CPU. So when we talk about high-level tools where you see visualizations and so on, you can actually count in a way. You can start have visualization of what threads are running at the CPU, and then you can count these events. So you can get a visualization of, oh, CPU is running thread 1, this is happening. Context switched, you're seeing thread 2, but you're getting the counts. So that's a separate activity on top you'll have to do based on what's happening at the system level, right, from a scheduler perspective. But there are all these ways that we can do that in LinuxPerf, but WindowsPerf, have you started?
Per core, it's only per core. So Windows kernel does not support PMU context switch. So Windows kernel will not track the process and its threads across the cores and count the PMU counters accordingly. No. It probably will happen soon, but right. It's not yet supported yet. So Linux kernel is different. In other way, I will not say better, I cannot say better.
Yeah,
for
so
legal
that's
reasons.
something to look into, is in LinuxPerf, at least the PMU events counting is tied with the scheduler task.
Yeah, it's context switch. Yeah.
That's probably what you were asking. But that's not exactly counting number of context switches, but this is more about counting PMU events attributed to a specific thread or process. And that is a separate enablement, but LinuxPerf does support that.
Yeah. Yes. Any other questions?
So when you install an event in the PMU for the user space process, when the user space process makes a system call to the kernel, and for instance, instruction count event, does that instruction count and the kernel executes on behalf of that process, but without context switch, it's the same process. Are the instructions being run in the kernel being counted? Or just the user space part?
That's a good question. So again, if we were going to count what's happening in CPU, it's just going to count what's happening in CPU regardless of what it is running. But in perf, we also have the option to count kernel and user space separately. LinuxPerf has that. So
WindowsPerf as well we have. Yeah. We have the flag, yes.
Okay.
Yes.
Yeah, so that's another way to kind of categorize, right? Kernel thread, what's happening, and user space. And then if you take that further, then user space can itself be running multiple applications or threads, but kernel Linux at least provides a way to categorize that. That's because there is a capability to tie your event counting to a task context or scheduler. So basically what's happening is when the way it works is that when you are asking to count for a specific thread, the process of the thread coming in context, where the scheduler, when it comes, brings the task to context, it also starts the event. And then when the task is gone out of context, it also stores the events, and that mechanism is enabled in Linux.
Yeah, it's we use a very similar hardware. So we only use the hardware PMU features of that. Yes, it's in a very simple way. In a way, when you use WindowsPerf, you have to assume you'll be running your workload with all the threads on one core for sampling. And no matter what's happening on this core, we're going to pick up everything, all the noise. The noise is usually marginal, especially on a 80 core and one CPU. 78 cores are doing nothing, and 2 are beating the drum. The 0 and 1 probably, yes. So yeah, in that way, yes. That's a limitation. But we can see that for this kind of analysis, in general, it works out. Like I said before, one has to take its application, take the workload from it, like an algorithm or a module, and run it consistently, like I was running that computation, and then have a consistent, saturates the event over the time. That makes sense. And it's a static analysis also, people forget. We run the workload when we stop, and then we analyze all the data, rather than in real time looking what's happening, right? So analysis, like I'm pinning Microsoft Edge to one core, opening the web browser, web page, and looking at the events, it's pointless. Yeah, that's not what we want to do. Yes, we first to use a different performance tools to see what was the startup, what was the I/O maybe, which modules are stalling, not like event stalling or CPU stalling, but which modules are taking a long time, maybe some rendering or whatever, and then look at the algorithm, maybe that is loading a picture, rendering a picture, or whatever is happening, yes. It's not easy. Yeah, the performance analysis is not easy. Okay, I think no more questions. Thank you very much. Again, we're going to have 2 more sessions about WindowsPerf. I'm just going to stay here probably.